In previous lectures, we talked about in-behavior and multiplicity, which leaves us with methods for determining the roots of a polynomial. Now, in previous algebra classes, you probably learned a variety of factoring strategies, but they were mostly limited to polynomials that had a relatively small number of terms. In the remaining lectures in this series, we're going to talk about more general methods that can be used to find the factors of larger polynomials. Now, when we talked about multiplicity and in behavior, our approach is very heuristic. That is, we just looked at some examples and situations and used those to kind of infer some general results. The concepts and theorems we're going to be using to look for the roots of a polynomial are a little less intuitively obvious. In other words, they need to be formally proven to be true. Now, with that in mind, the next set of lectures will come in groups of two. The first lecture will go over the material from a theoretical perspective, proving things when necessary. And the second lecture will look at specific examples so you can see how the tools are applied. Now, if you're just looking for practical tools, you won't come to any harm from skipping over the theoretical bits. However, if you're going to be moving on to more complex math classes, I encourage you to at least listen to those parts and try to follow along. Now, this is the classic division algorithm for numbers that comes from number theory. This is actually our definition of division for integers. So to see how this works, think about an example like 13 divided by 5. Right? This is a little quick long division shows that this is equal to 2 with a remainder of 3. In other words, 13 equals 5 times 2 plus 3. So now you can see how the numbers from the division fit into the algorithm's formula. The Q is the quotient and the R is the remainder. All right, the polynomial version looks more complicated, but it's really saying the same thing. If we want to divide f of x by g of x, then the result is the quotient q and a remainder r. Now, in the numeric version, the remainder had to be less than the divisor. Right? Well, we've got a similar requirement here with smaller being determined by the degree. So that's what the part that says the degree of the remainder has to be less than the degree of g means. Now, to prove this, we're going to have to show two things. First, that for two initial polynomials, f and g, polynomials q and r exist where f is equal to g of x times q of x plus r of x. And second, we need to show that the q and r polynomials are unique. Now, I'm going to warn you up front. If you don't have some experience proving things already, this one is going to seem a little complicated. But don't let that warn you off. The polynomial division algorithm is required to prove the remainder and factor theorems, which are the two tools that we'll actually be using. Now, those two proofs are much more straightforward. So even if this one has you a little baffled, carry on to the next two. And I think you're going to find that they're more accessible. So how can we prove this? All right, the method we're going to use is called mathematical induction. And specifically, we're going to do this on the degree of f. All right, so you remember how mathematical induction works. First, I'm going to show that the statement is true for n, that's going to be the degree, for the degree equal to 0. Sometimes we'll also show it for 1 if 0 is kind of a trivial case. That's the first step. Then the second step, I'm going to assume that the algorithm is true for n minus 1. and I'm going to show that that means it has to be true for n. And that covers all my cases then, right? Because if it's true for 0, it must be true for 1, and if it's true for 1, then it must be true for 2, and it's true for 2, it must be true for 3, and so on. So that covers every possible integer degree, and those are all the possibilities, right? So at that point, I'll have shown what I needed to show. Okay, so how are we going to do that? Well, first, I have to do that initial case, right? So to start off with, assume that the degree of f is less than or equal to the degree of g. Right? So these are the small numbers. For example, f could be 0 or 1, something really small. All right. In this case, the existence of q and r are really kind of trivial. I'm going to take q of x equal to 0. Then that means f of x equals g of x times 0 plus r of x. So f of x is equal to r. Or really more specifically, remember it's r and q that we're trying to find. So I would say r of x is equal to f, and that does satisfy our requirement here, right? Because our initial assumption was that the degree of f, and therefore the degree of r, must be less than or equal to g. All right, so that's the first part. We've shown that this is true for small degrees, right? Degrees that are less than g. All right, so now what happens if the degree of f is greater than the degree of g? All right, well, remember our assumption here, assume the statement is true if the degree of f is equal to n minus 1. And I want to show that this must then be true if the degree is equal to n. All right, so let's see. To start this, I really need to be specific about what these polynomials are. So let f of x equal a to the n, x to the n, plus a to the n minus 1, a sub n minus 1, x to the n minus 1, plus so on out to a sub 0. And we're going to let g of x equal to b sub m, x to the m, plus b to the m minus 1, x to the m minus 1, plus so on out to b sub 0. All right. So here's what I'm going to do. I'm going to create a new polynomial. Right? I'm going to create a new polynomial. Call it f prime of x. Now, some of you, if you've maybe taken a calculus class, that prime does not mean the derivative of f. Right? In calculus, that prime always means the derivative. Other branches of math also use it. Right? And outside of calculus, it just means a new function that is somehow derived or calculated from the original f. Right? So my f prime is going to be the original f of x minus an over bm x to the n minus m times g. Right, now, I know that seems a little weird, but I picked that really carefully. You need to convince yourself that this new polynomial, this f prime, has degree n minus 1. Right, and to see this, let's write this out. F of x is a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, and so on. All right, and this is minus a to the n over b to the m, x to the n minus m, times g, and g is bm x to the m plus bm minus 1 x to the m minus 1 out to b0. All right. Now think about what happens here if you multiply this out. If I take this a to the n, b to the m piece, and I distribute it into here, this term becomes minus the b to the m's cancel, so all that's left here is a to the n, x to the n minus m times x to the m. You add the exponents, and that becomes x to the n. Right, and the next term becomes, sorry, it's not a plus, it's going to be minus. It becomes minus a to the n, it becomes some new constant, right? Call it c, x to the n minus 1, plus a bunch of other stuff, and I really don't care so much about the details there. Now, I still have all of this f bit here, a to the n, x to the n, a to the n minus 1, so on. Now look at what happens. I have a to the n x to the n minus a to the n x to the n. These x to the n terms go away. And all that's left is a polynomial whose biggest term, whose biggest exponent, is n minus 1. That's what I needed you to see. The degree of f prime is n minus 1. All right, so let me clean this up here now that we've seen this piece. Right, so what does that mean? Well, remember, my induction hypothesis says that the division algorithm works on a polynomial if the degree of f is n minus 1. All right, so this means there exist polynomials q and r such that f prime of x is equal to, let's call it q prime. Q prime of x times g of x plus r of x. Okay. So what? That doesn't look real helpful. Okay, but look, it is. All right? It is. Here's what I'm going to do. Right? I am going to define another polynomial. Right? I'm going to define a polynomial, q of x, that's equal to q prime of x plus a to the n over b to the m x to the n minus m. All right, now we're getting there. Look at, let's take a look at g of x times q of x plus r of x. Right? I want you to think about what this equals. All right, all I'm going to do is I'm going to take my definition here and substitute that in for q. So this becomes g of x times q prime plus a to the n over b to the m x to the n minus m plus r. Right, now let's distribute. Right, get rid of the brackets here. This is g of x times g prime of x plus g of x am, excuse me, that's an n, sorry, a n over b sub m x to the n minus m plus r. All right, but now wait a minute, look. G, this is a q prime here. G times q prime plus r, that's this line right here. That's f prime of x. All right, so let's put that in here. This is f prime of x plus this messy thing here, g of x a n over b m x n minus m. All right, that did it. Look back up here at this line. Right, if you take this a n b m part, add it to both sides, move it over to here, you get this expression that I have right here, and that is equal to f of x, and that's what I needed. F of x is equal to g of x times q of x plus r of x. There's my q. My q is this expression here. R is the original remainder from up here. And remember, when I came up with that r, that was based on the division algorithm. So the degree of this r is less than the degree of g. And that was what I needed to show. So that leaves us with a question of uniqueness, right? Are these Q and R polynomials unique? And this is cleaner, right? This is definitely going to be a little easier to show. And we're going to do this in kind of the classic way. We already know we have this original Q and R. Well, okay, let's assume that there's a second Q and R, right? Let's call them Q1 and R1. So not only does f of x equal g of x times q of x plus r of x, but f of x also equals g of x times q1 of x plus r1 of x. Okay, well, if that's true, if both of these things are equal to f, then they must be equal to each other. So g of x, q of x plus r of x must also equal g of x times q1 of x plus r1 of x. All right, so what I'm going to do here, I'm going to rearrange things a little bit. I'm going to bring the r's onto one side and everything else onto the other. So r of x minus r1 of x equals g of x q1 of x minus g of x q of x. All right. Okay, now let's factor the right-hand side. Let's factor out a g. So g of x times q1 minus q is equal to r of x minus r1 of x. Okay, so now we have two possibilities here. All right, either q1 of x minus q of x equals 0, or it doesn't equal 0. All right, well, look, one more thing here. If these two polynomials, right, this one and this one are equal, then their degrees must be equal. So the degree of r minus r1 has to equal the degree of g times q1 minus q. All right, now think about those two cases, right? If q1 minus q is not equal to 0, then this polynomial is g of x times another polynomial. That means the degree here is at least equal to the degree of g. But that's a problem, right? The degree of r minus r1 has to be less than the degree. This should be a g up here. Has to be less than the degree of g. Okay, which means that's not true. It has to be the other case. q1 minus q has to be 0, which means that my new q1 is actually the same as q, right? And let's see, come back up to this line here. If, excuse me, not that one, this line here. If q1 minus q is 0, then r minus r1 equals g times 0, which is 0, which means r and r1 are also the same. So there are in fact there's only one q and only one r that satisfies the requirements of the division algorithm. So this brings us to the two practical theorems that we can really use to answer this question: is a linear factor, something like x minus c, a factor of a polynomial, or isn't it? And the first step in doing that is this thing here. It's called the remainder theorem. But what this is it gives us a really quick way to determine what the remainder is when you divide a polynomial by a linear polynomial, something like x minus c. Right, so here's what we're going to do. We're going to use the division algorithm. Right, the division algorithm says if I divide p of x by x minus c, then there have to be polynomials q and r such that p of x equals q of x times x minus c, that's the thing I'm dividing by here, plus r of x. Right, and specifically, remember that the division algorithm says the degree of the remainder has to be strictly less than the degree of the thing that we're dividing by. That's x minus c. But the degree of x minus c, that's a linear polynomial, that's just 1. So the degree of r must be less than 1, and there's only one possibility there. That means that the degree of r must be 0. Right? In other words, r is a constant. Right? It's just a number. Okay, so let's write it that way. That means that p of x equals q of x times x minus c plus, and I'm going to use a capital R here to really help distinguish that from the polynomial r. All right, now remember, keep this firmly in your head. I want to know what r is, right? That's my goal here. All right, well, here's what I'm going to do. I'm going to evaluate this polynomial for x equals c. Right? And if I replace the x with a c on the left side, I have to do it on the right side. But look at what happens here. C minus c, that's just 0, which means this whole term is just 0, which means p of c equals r. Or let's turn this around, right? Because it was r that we were trying to find. R is equal to p of c. In other words, if I want to know what the remainder is, when I divide p by x minus c, all I have to do is take c, this number here, substitute it into the polynomial, and see what I get. So this really brings us to the heart of the lecture. Right? Remember what our goal has been all along. I want to answer this question: is x minus c a factor of my polynomial, or isn't it? Right? And the factor theorem is the tool I need to answer that. The factor theorem says x minus c is a factor of p if and only if p of c is equal to 0. All right, so this is a good one for us to look at if you're kind of new to proving things. This if and only if here, it sounds like we're just trying to emphasize the point here, right? But it isn't. This is a technical term. Right? When you see if and only if in a theorem, that means there's actually two theorems in one here. Right? The first one is if x minus c is a factor, then p of c equals 0. And the second theorem is it's the converse of this. It's this theorem flipped around. If p of c equals 0, then x minus c is a factor. So there's actually two things that I have to prove here. All right, so let's take a look at the first one here. I know that x minus c is a factor, and I want to show that that means that p of c is equal to 0. All right, well, remember what it means to be a factor. That means I can multiply x minus c times some other polynomial and get p. There is no remainder, right? If a number if a polynomial is a factor. All right, but now just evaluate this at c. P of c equals c minus c times q, but c minus c is 0, which means this whole thing is 0, and that's what I needed to show. Right? P of c is equal to 0. All right, now how about this side? Right? I know that P of c equals 0, and I want to show that x minus c is a factor. All right, well, let's apply the division algorithm here. P of x is equal to q of x times, not r of x, q of x times x minus c plus r of x. And let's see, what do we know here? Now, the remainder theorem, that's the division algorithm. The remainder theorem says that if P of c, or it says that P of c is the remainder when you divide by x minus c. But I know that P of c is equal to 0. Well, that means that the remainder is 0. So if I put 0 in here for x, this becomes P of x equals q of x times x minus c, which means x minus c is a factor. And that's what I was looking to show. So now that we finished the theory, right? We've derived these theorems, in particular that last one, the factor theorem. What comes next? Well, in the next lecture in the series, we're going to look at some specific examples. Right? We'll see how we can use the remainder theorem to quickly determine the remainder when a polynomial is divided by a linear factor, and we'll see how we can use the factor theorem to answer this key question: is x minus something a factor of a polynomial, or isn't it?